1. Okay, differential equations, 2.6, last lesson of our chapter. We're going to come back to not exactly solving a differential equation here, but rather getting an estimate to a solution that would solve that. So obviously there will be some general curve that we can work with. We're going to start with an initial point, and then we can go ahead and get an estimate for what we would anticipate. For example, we'll be given a differential equation, dy dx is equal to x plus y. We're going to be given a point on the solution curve. We don't know what the solution is. It's 1, 1. And we're essentially going to use tangent lines iteratively, repeatedly, to extend to get to other points. And we're going to go with a step, that's our delta x of 0.01. We'd like to estimate what y of 1.05 is. You can really remember, as you see at the top of the screen, that essentially Euler's method is working with this differential, that dy was equal to f prime of x dx. It's just that dy we could say is approximately delta y, and where we have dx we could put in delta x. And what you do for Euler's method to get these estimates, you pretty much go through this table. It's a very mechanical process where we're always going to start with a point. In this instance, we're going to start with 1, 1. And our delta x is going to be 0.01 repeatedly all throughout this process. We're always going to keep uniformity, go up the same number of steps for delta x. But to find delta y, that's that differential formula. We'd say, how much would our y change as we move over this much with x? Well, we'd have f prime of x. F prime of x is really what we have for our dx. And you can see that's what I had written slightly above our f of x. When you want to find that, that's coming right here. That's where we're actually using our differential equation. We're going to plug in the point 1, 1, and I think we know that, a 1 plus a 1 in this instance is simply going to get you a 2. So we'll say it's 2 times a 0.01, and we know that 2 times 0.01 is 0.02. Then what? We come back over here, we'll say take your original x, which is 1, add to it a 0.01, take your original y of 1, add to it your delta y, which in this case is 0.02. You have a new point. That new point is 1.01, 1.02. Then we're going to continue. We're going to do the exact same process that we just did. And that's what I mean when I say Euler's method is so mechanical. It's really just doing the exact same steps. We've got a 0.01 for delta x. It's just that this time when we're finding delta y, what's going to happen? Well, we're going to take our x plus y. Here's your x plus y. What do you get when you add 1.01 and 1.02? Well, a 2.03. And then we're going to multiply by 0.01. Now, multiplying by 0.01 is effectively going to take your decimal point and move it 2 places to the left. You're really multiplying by 1 over 100. So as we move our decimal 2 places to the left, you'll have 0.0203. Okay? Well, then what? We're going to say take your original x, which is 1.01, add to the change of x, which is 0.01, take your original y, which is 1.02, add to that your 0.0203, and what's your new point? Well, 1.02, and then over here we'll have a 1.0403. Well, how do you know when you stop? Well, you're going up to 1.05. That's where we're headed. So it looks like we're going to have to do Euler's a few more times here, right? And that's okay. We can definitely, repeat this. It's very mechanical. Your delta y, you're effectively saying, find that tangent line slope. Take your x plus y here. Well, you add 1.02 and 1.0403. It doesn't take too long. And by the way, if numbers are getting to be a little bit ugly, and forgive me, I just made a typo, righto, I guess you could say, 2.0603. As you do that, feel free to use a calculator as these numbers can get a little ugly. But multiplying by 0.01, guys, you're just going to slide your decimal 2 places to the left. So you'll have 0.20603. Now what? Take your original x, which is 1.02. Add to the change of x, that's 0.01. Take your original y, which is 1.0403. Add to that your 0.020, and now it's going to maybe get just a little bit ugly. Not for your x, I hope. I hope you can see pretty nicely. You get 1.03. But let's see here. We've got the 4, the 3, and the 6 are matching up right here. So if I've done this right, I think we're going to get 1.060903. Feel free to confirm that with a calculator. You get the idea that you're going to be able to just continue doing this pattern. So now we're at 1.03 and our 1.060903 numbers are beginning to get kind of ugly right now, stating the obvious. Add these two things together. Well, the 3's in the 100th place right here. I think you can see pretty quickly, 1 and 1, you'd get a 2. You'd get 2.09 and then a 0903. And things are beginning to get kind of tight here. We'll get, as we multiply by the 100th, 1 over 100, you get 0.02090903. Well, here we go again, 1.03 plus your change. And then we've got our 1.06093 plus 0.02090903. Maybe it's at this point, maybe you'd feel more comfortable breaking out that calculator, and that's perfectly okay. There will be some differential equations, guys, where just got to tell you, the numbers aren't as easy to type in, and that's okay. It's definitely okay to have your calculator out here. We went a long way without it, after a while, I think you're going to see that, we're just getting a pretty big mess here. About 1.0813903, I guess, is what we're getting. Let's see, bring that thing back. 1.08183 and then 903. Wow. If I've done that right, you guys getting the same thing? Yeah? All right, so one more iteration. How do we know we have to do one more? Well, we have to get up to 1.05. So we're going to have over here 1.04, and here's your 1.081833903. My gosh, look at all that. So, wow, if we're just adding those things together, tell you what, you already had your calculator out. How about we just keep that same thing we just had and say plus 1.04, make life a little easier on us. And we'll get about 2.12183, something like that. Let's see, 2.12183. 9 and so on. After a while, you can think, well, my gosh, we're just more or less dealing with getting super accurate. We'll probably just go to 3 decimal places at the end, or sometimes the author might ask for just a little bit more. But like if you multiplied through by 0.01, you can see that's pretty much what we've got. Looks like we'd have an 0.3 here. But to finish this up, we're going to have 1.04 plus 0.01. Our original was 1.0818390. Something like that, and then we're adding to that a 0.0212183.903. My goodness. Well, it's just going to be a matter of patience to get this thing up here. If we had that, evidently we had that 0.02 form right there. We're going to add that to 1.08183. Yes. Oh, did I goof that up? Here, let's go ahead and just type it out as we see it. Yeah, evidently I made a typo. Yeah, thank you. Easy to make a mistake here, isn't it? Especially if you're rushing through. And as we just continue on, you just have to be patient calculating this out. I think a bigger question is, how accurate is Euler's method? Euler's method, amazingly, is very accurate. You can see that we're getting a 1.103. And, after that, we'd have 0.57, something like that. And here's your 1.05. As long as you're staying relatively close to your initial point, you'll find that Euler's method gives a surprising estimate for what you're working with. This is a problem where maybe you wouldn't be able to get a solution to the differential equation, but you can still walk away feeling pretty confident that you're in the right ballpark for an estimate on that curve. Okay, so